Hello everyone, welcome back to Electronics 1. In the last class we introduced a more robust model for modeling the BJT or the bipolar junction transistor in saturation mode. But today we're going to return back to forward active mode and introduce common models used to represent the BJT when operating with large signals applied. Okay, these models are known as the T and the pi models. And let's just say we'll just put these are the large signal models. We'll see a little later on in the course we'll evaluate or come up with a modified model for small signal operation. So much like we did with our diodes when we had two versions of the model, a large signal and a small signal. Okay, so from the equations that have been introduced over the last few lectures, we can come up with a model to represent the diode, the BJT, and to more simply represent it in a circuit and solve for its operating conditions. Okay, and this again is specifically for the forward active mode. So in the forward active mode, a simple T model, as it's referred to as, looks like this. So we represent the base to emitter junction as a diode, and a real diode whose characteristics are exponential in nature, but the collector circuit is represent as a controlled current source that's a function of well, you can look at it from one of two perspectives. It's a function of the input current, or you could look at it as a function of the input voltage. Okay, so this representing the collector, this representing the base, and this representing the emitter. Okay, so if I label my currents on here, oops, this is my collector current. Let's do this as a lowercase. This representing my emitter current, and this representing my base current. But as we know, this collector current is also equal to my alpha times my emitter current. Okay, and this collector current we discovered is equal to some saturation current times e to the VBE, so function of the base to emitter voltage divided by thermal voltage. Okay, but we also said that it's related to the base current. through the common emitter current gain. Okay, so this might be thought of as a voltage controlled current source or a current controlled current source, depending on your perspective here, depending on whether you consider VBE to be the input or whether you consider your base current to be your input. Okay, and the VBE is that voltage from, of course, base to emitter. This diode that we're representing in the base to emitter circuit, because the current flowing through it is the emitter current, its saturation current is going to be equal to the saturation current shown in the collector circuit divided by alpha, or divided by our common base current gain. Okay, and again, we know that this emitter current here is equal to this saturation current, E to the VBE divided by VT, but the saturation current is divided by alpha. So these are all the equations that we developed over the last several lectures. Okay, so this is our T model to represent a BJT with a large signal applied. And as I said, this can be considered as a voltage controlled voltage source or a current controlled current source. The voltage controlled voltage source, right, if you look at the relationship here, when we think of it as a voltage controlled device, we see that the relationship, there's an exponential term in there, so this relationship is nonlinear, so it could be considered nonlinear voltage controlled current source. I may have just said voltage controlled voltage source, but I meant to say voltage controlled current source, right? It's voltage controlled current source. Or if you focus on this relationship between base current and collector current, we can think of it as a linear, because they're related through the common emitter current gain beta. So in that case, it's a linear relationship between the input current and the output current, or treat if referring to the base current as the input and the collector current as the output. Okay, so in this case, we can treat it like a current controlled current source. Okay, so we have kind of two options here. Okay, so that's our T model. If we take this model, we can it can be modified by dragging the base to emitter diode. Let's say we can morph this model by taking that base to emitter diode and dragging it into the base lead. Okay, when we do that, that's going to mean that that diode is going to now see the base current rather than the emitter current, so we have to modify the diode characteristics accordingly. Okay, so however current is now the base current rather than our emitter current. As I said, the diode characteristics will have to be modified appropriately. Okay, so what this looks like when I take this T model and drag the diode into the base lead, I get a model that looks like this. Okay, so now the characteristics of this diode, which has base current flowing through it, this diode must have a saturation current that's, again, the saturation current being set by that collector to base junction, and that saturation current is now scaled by beta because our current in our base lead is beta times smaller than that in our collector lead, right? Okay, and just let me label this, still representing the collector, emitter, and base here. Okay, if I take and rearrange this into what we might call a two-port network, so by that I mean it has two input ports and two output ports. So I end up with a, oops, give myself a little bit more room here. I can treat the input as being from base to emitter, across this diode that I said is carrying the base current here and who has a characteristic that is a function of the saturation current of the collector circuit divided by beta, and making the emitter common to both the input and output. I have an output circuit that is the controlled current source between the collector and the emitter, and that current source is a function of our base current. It's in fact our base current times beta. Okay, so in this case, so we have a two-port network now where this left-hand side is our input, and of course the output is taken from the right-hand side. This model or means or model for representing a BJT when operating with a large signal is known as a pi model. Okay, so in this arrangement it's clear to see that the device can be shown and separated into input and output. Output circuit, where, as I said, the input is applied across base to emitter, and the output is taken across the collector to emitter. Note here that the common terminal is the emitter. And the factor that links the input and the output here is this term beta, and that's the reason behind this factor being referred to as our common emitter current gain. Okay, so using this model and this two-port network, we have a fairly well-defined input and output behavior. So let's look at the input and output BJT characteristics. So if we focus initially just on the input circuits, well, the input circuit is just a diode, represented just by a diode, where the voltage across this diode is the base to emitter voltage, and of course the current through that diode is the base current. So not surprisingly, the input characteristic is going to be identical to that of a diode, except here we represent our diode current as the base current, and the diode voltage is the base to emitter voltage. Okay, so this, as I said, looks identical to what we would see for any diode. Okay, and of course the operating point of this diode determines our or maybe I should say the base to emitter voltage is going to determine the base current. Okay, so we've shown this is kind of indicating a DC operating point or a bias point, shown here by the dot. We sometimes refer to this as Q. This exponential here we know is a function of the saturation current of our transistor times e to the VBE over VT. Okay, we stated this up above. Here we said that the saturation current was scaled by beta, because this saturation current, this is the saturation current for the collector circuit, and that collector, the base current is equal to the collector current divided by beta. Okay, so that's where that beta in the denominator comes from, that common emitter current gain term. Okay, let's look at the output characteristic of the BJT. The output characteristic, at least at first glance, is very simple to model. We have a controlled current source here between the collector and the emitter, and that current through the collector as a function of the voltage from collector to emitter is constant, right? The collector to emitter voltage has no impact on the current, because the current is controlled by the input. So in that way, if we look at the characteristic, IV characteristic of the output, where the current axis represents our collector current, our voltage axis represents our collector to emitter voltage, our output is going to be just a straight line that, of course, is a function of the base current. I'm going to use a uppercase I here because we're referring to a specific base current or a specific bias point. Okay, as that base current changes, this output characteristic, of course, will change as well. So for different base currents, we're going to get, maybe we'll call this 1, 2. So the output characteristic again is impacted by that input operating point. Okay, but this output characteristic fails to take into account the fact that in order for us to stay in forward active mode, which is what we are assuming with all these models, these are models for forward active operation, that the collector to emitter voltage must not drop below our saturation voltage, which we said was approximately 0.2 volts. Okay, so however, remember that for IC to be equal to beta times IB, we have assumed forward active mode of operation, right? Those equations only apply when we're in forward active mode. Okay, and this in turn assumes that VCE is greater than VCE sat. And this being a fixed value, I should show this as uppercase here. Okay, so when we take that into account, the output characteristic, so this output characteristic, this is not quite right. Our output characteristic, when we account for that our collector to emitter voltage must stay above saturation, we can develop an improved output characteristic that takes into account VCE sat. So VCE sat, and it ends up looking kind of like this. And again, you can develop a family of output curves here that are dependent on the specific base current. Okay, so this being maybe base current 1 versus base current 2. So these are all just different operating points that will impact the operating point of the diode. Okay, and here I'm showing that base current, I'm assuming that base current 1 is higher than base current 2 and is higher than base current 3. Okay, and as we know, this VCE sat, this is somewhere in the vicinity of about 0.2 volts. Okay, so now we have an improved output characteristic that takes into account that this collector to emitter voltage can't drop below about 0.2 volts. Okay, so that's our T and our pi model for representing a BJT under large signal operation. We are going to revisit a slightly modified version of those models as we look at small signal operation of the BJT a little bit later on. This output characteristic still isn't quite correct, and we're going to evolve it a little bit more in the next class as we account for what's known as the early effect.